Hello guys, in this video I am going to solve this question number 41 of chapter 7 from this book Engineering Circuit Analysis by Hayt, Kemmerly and Darwin. So the question says that for this circuit we need to reduce the network to the smallest possible number of components. If each inductor is 1 nanohenry and each capacitor is 1 millifarad. So over here simply we need to use the formulas to get the equivalent capacitor and equivalent inductor. So just a quick revision that we know that for the capacitors, if capacitors are in parallel, then the formula of C equivalent it is C1 plus C2 Cn. Whereas if they are in series, then the formula is 1 upon Ceq equals to 1 upon C1 plus 1 upon C2, or simply we can write, if you solve this particular, so simply you can write C1 cross C2 upon C1 plus C2, right? So this is for the series, right? And for the inductor, we use exactly the same formula that we use for the resistors. So if the inductors are in parallel, then the formula is 1 upon L equivalent equals to 1 upon L1 plus 1 upon L2, right? And this, like if you solve this, then you will get L equivalent will be L1 cross L2 upon L1 plus L2. And similarly for the series, again we follow the same thing that we follow for resistors. So R equivalent in series, sorry, not R, L, it will be L1 plus L2. So following this formula, considering this formula for the capacitor and for the inductor, we are going to reduce this. So to reduce this, like if you look at this part of the circuit, right, or just this part, over here we have a two capacitors. So we have two capacitor, and the values of the capacitor of all the capacitors, it is 1 millifarad. So if the two capacitors are in series, so the equivalent, like this, the equivalent of this, it will be we are going to get, it is 1 millifarad, it is 1 millifarad. So the formula that we are going to use, it is this one, right? So simply it will be 1 into 1 upon 1 plus 1, so we will get 1 upon 2 equals to 0.5. So we will get 0.5 millifarad, right? So this part can be replaced with millifarad. So let me put it. Our circuit, like it can be reduced to this one, right? And over here let me draw the remaining circuit. It is this, then and this is the circuit, right? Over here we have this and then this, right? And now after that we have this capacitor, so I will draw this capacitor. Let me reduce. So it is this capacitor. After this capacitor we have another parallel branch with two capacitors and two capacitors, so I will draw that also, this and this and this and this, right? After that we have another parallel branch with single capacitor, right? So I will draw this single capacitor, and then last we have one inductor, so we will put this one inductor, right? And then this is short circuit, so it means this, and from this short circuit we have this 2, so we are going to put these two. So this is our circuit, right? And it is 0.5 because this, like, we have combined this to get 0.5 millifarad, right? So it is 1 millifarad, it is 0. The capacitors all are 1 millifarad, 1 1 1 1 1, right? And the inductors, they are 1 nanohenry. So let me put the values 1 1. Right? So over here now we can combine these two. So over here, since the two capacitors are in parallel, so our formula is this, C1 plus C2. So simply we are going to combine. So if we combine this, we are going to get 1 plus 0.5. So it is 1.5 millifarad. So if I modify this capacitor, let me put it as 1.5 millifarad, right? And remove this one and remove this particular branch, right? So it is this. Now coming to this part over here, let's complete the capacitors. So over here in this branch we have two capacitors in series, right? So again, using the series formula, which is this one, so we will get our C equivalent. It will be, for this case it will be 1 into 1 upon 1 plus 1. So it is 1 upon 2, it equals to 0.5 millifarad. So this complete, it can be replaced with 0.5. So if I just make a change over here, it is 0.5 millifarad. Similarly, this two branch also we can replace it with 0.5 millifarad. Right? Now after this now we have this 4 capacitors in parallel, right? So using the formula for the parallel capacitor, and the formula is this one. So simply we need to add all the values. So if we combine all this, so over here we have 1 plus 0.5 plus 0.5 plus 1. So we get 3, right? So we get, for this, we get 3 millifarad. So we can replace these 4 capacitors with a single capacitor. So let me remove this complete thing. So we will have only one, and the value is 3 millifarad. Now after this, now we can come to the inductors, right? Now in the inductor, you can see that on the left side, like over here, we have this too, right? And for the inductor, the parallel inductors are combined using this formula. So using this formula, we are going to get the equivalent inductance, which will be 1 into 1 upon 1 plus 1. So it will be 1 upon 2 equals to 0.5 nanohenry, right? So we can remove one inductor, and the value can be changed to 0.5 nanohenry, right? Now coming to the last part, over here you can see for this particular case, now or just if I do the combination of these two. Now these two are in series. So in series, it means we need to add the two inductance value to get the equivalent resistance. So 1 plus 1, it will be 2. So I can replace this with 2 nanohenry. Now, but if you look at this over here, it is short circuited. This particular inductor, it is short circuited, and since it is short circuited, so it means no current will come through this inductor. And since no current is going to come over here, so simply we can remove this inductor, right? The presence of this inductor is useless because no current is going to flow through that. So overall we just have this 1 nano henry over there. And now this is our reduced form. This is our reduced form, having one capacitor, having one capacitor over here, one inductor over here, one inductor over here, one this, one this. Now we can further reduce it. You can see this inductor and this inductor, they are in parallel. Like if we interchange the position of this capacitor and inductor, then this, like we can like redraw, we can draw this, we can bring this inductor towards this side. So now I can remove this, and now we can do the combination of these two. Now since these two inductors, they are in parallel, so using this same concept, we get a final equivalent as 0.5. So it means we can remove one inductor. So if I remove this one, so and replace it with the equivalent this, so I will get this. So let me remove this one, so it will be this. So now this is the reduced form of the given circuit, of this circuit. We cannot, you can see that we cannot reduce this circuit further, because we have one capacitor over here, one inductor over here, and then this inductor and capacitor, they are in parallel, so we cannot combine them, right? So this particular, it is the reduced form of the circuit, right? So if you have any doubt, you can put it in a comment box. Do subscribe my channel and share this video with your friends and colleagues. Thank you.